Okay, this is example 17.10 for Moore's circle. Here we're given a stress element as shown right here. We have tension in both the y direction and in the x direction, and we also have shear at this point. We're going to determine the magnitudes of the principal stresses and the maximum shear stresses. We're going to determine the orientation of the principal planes and the planes on which the maximum shear stresses occur. And we're going to show the results of the two previous parts by drawing new rotated stress elements for both the principal planes and the maximum shear plane. Okay, so we start by knowing that our sigma in the x direction, our stress, normal stress in the x direction is 10,000 psi, tension, that's right here. We know that sigma y is also tension, is 13,000 psi. We know that tau is plus 6,000 on the vertical face. That's right here. Okay, so that follows our convention that says if the shear stress tends to rotate the element clockwise, it's positive. Okay, if it tends to rotate the element negative, it's counterclockwise. So when I'm looking at this one right here, I'm looking at the vertical face. It goes with x. That tends to rotate my element clockwise. So therefore, it's positive. Whereas if I'm looking at the horizontal face here, that tends to rotate the element counterclockwise, therefore negative. Okay, so we're going to construct our circle. The y-axis is going to be shear stress. The x-axis is going to be the normal stress. We're going to plot sigma x at point G and sigma y at point H. I'm going to try this on the x-axis where tau equals 0. So I tried this one right here. H is right here. H is right here, and that is our maximum, our shear stress, our bending stress, 13,000 psi is plotted here at point H. And then our normal stress, sigma y, is plotted here at 10,000. Okay, so what I got is 10,000 and sigma of 6,000 here. That's my coordinates of point x. Okay, so here is my x state, which is both this 10,000 psi, 10,000 psi, 10,000 psi, plus 6,000. And then y is down here. Okay, y is going to be our 13,000. I got these x and y's backwards here, sorry. Our y here is going to be this 13,000 and minus 6,000. Okay, so I got this point x, I got this point y. The center of Moore's circle is going to be this point M. We always label that point M. So G to M is going to be sigma x minus sigma y, sigma y minus sigma x divided by 2 is 1,500 psi. So 1,500 psi, that's this one, 1,500 psi, 1,500 psi. So that is the distance from G to M, and it's also the distance from M to H. Okay. Now that we have that, we can find what the radius of Moore's circle is, and that would be this my, the distance from M to y. And really what we're going to do is we're going to find this out. This M to y is really just using this triangle right here. So M to y is the hypotenuse. We know M to H is 1,500 psi right here. We know that H to y is this negative 6,000. It's our shear stress. Okay, from that we're able to find what this radius of Moore's circle is. So our radius of Moore's circle is 1,500 squared plus 6,000 squared is 6,185 psi. Okay, so now that we know what that radius is, we can find our principal stresses, because we know, first of all, what the distance from O to M is, O to M, and then now we know what the distance from M to Y is. So if we put that distance from M to Y, that gets us out here to our maximum principal stress. So O to M plus M to Y gets us out on this outer radius of the circle. Okay, so that gives me 17,685. And then sigma 2 is OM, again, minus the MY. OM minus MY gets us back to the sigma 2, which is going to be 5,315 psi. Now, isn't that a little bit easier than the formulas of 17.7? Okay, so I'll put this one out here. Here's the solution from your example in problem in the textbook, so you don't have to look at my graph here. But one more thing I want to point out to you about this graph is, yeah, we're using similar triangles here to find certain things. Okay, so our similar triangles that is this triangle right here? We're using that to find what it is. Now, we're doing this not necessarily 100% graphically, because our scale is all wrong. And why do I say that? Because look at this. Our tau here is 6,000 psi. So that's 6,000 psi from G to X. Okay? But if we look from M to G, that's 1,500 psi. You know, our scale is way out of whack. But it's okay, because we're using the Moore's circle as a construction vehicle to determine what our stresses are. We're not drawing it to scale. We're just using it as a picture, if you will, to help us understand what our stress states are. So 6,000 and 1,500, you can tell just by looking at this, it's not drawn to proportions. Okay, so now what we have to do is find the principal stress planes. And I've put this one out here. So essentially what we're talking about here is that the Moore's circle represents the state of stress. Points on the Moore's circle represent the shear stress, the normal stress, and then the angle at which those things exist. Okay? So when we're looking at this one, our original problem statement, when I say original problem statement, I'm going back to this stress element right here. Our original problem statement is that stress element. So that stress element exists on our Moore's circle as two different points. It's this point X and then this point Y. Those are the points that are defined by our original problem statement. Okay, so once we look at this one right here, we can see that if we were to rotate our point X up to point L through this angle 2 theta S, that gets us from our state of stress in the problem statement up to our maximum plane of shear, because this high point here on the circle is our maximum shear stress. So if we were to rotate our Moore's circle by this 2 theta S, we get from point X to the maximum plane of shear. If we were to rotate point X all the way about this 2 theta P1, we get X and rotate it up to Q, and that gives us our maximum principal stress. Okay? If we were, see, P1, maximum principal stress. And then this 2 theta P2, if we were to rotate point X down to this point P through this angle 2 theta P2, that gives us our minimum principal stress. So again, Moore's circle is a way of looking at the stress state of the element and then being able to look at it at all of these different angles right at the same time. Now, I hope you realize that what our plants, our way of calculating this principal plane stress here was a whole lot easier than what we did in 17.7. We pretty much had to guess and check what our angle was, because the tangent wasn't in, tangent was negative. It could only be in 2 quadrants. And when we're doing Morse circle here, it's fairly apparent. We say I need to rotate this point X all the way to point Q to get to my principal planes. So in that respect, it's a whole lot easier. Okay, so our principal planes, 2p theta equals the inverse tangent of 6,000 divided by 1,500. Okay, so again, I am just looking at this 2 theta p2. I'm looking at this triangle XMG, and that gives me 75.96. And then when I look at this overall, my 2 theta p1 will be 180 minus this 75.96. Divide by 2, I got 52 degrees clockwise. Okay, so I'm going to draw my principal elements here. I got 5315 in this direction in tension. I got 17,685 in this direction, and I got 52 degrees. So here is my element that I'm drawing based on principal. So what you notice on the principal stress element, there are no shear stresses. Okay, it strictly exists as normal stresses at that orientation. Okay, and then here's our maximum shear element. So what we've done is we've calculated our maximum shear stresses. We calculated our maximum shear stresses as this 1100 psi. And then I calculated this 2s using this equation right here. So we had 2 times theta p2 from this triangle here, and if we subtract that from 90 degrees, we get 2 theta s. Okay, so 7 degrees positive clockwise right here. Okay, so that's how we solve Morse circle problems for the general state of stress in a point.